So during the session, we have 4 talks, each talk of 30 minutes. All of the talks are online. And the first talk will be done by Libor Šmejkal from the Mathematical Institute of Physical Complexes, Dresden. The talk is entitled Altermagnetism and Spin Symmetries. So Libor, if you are ready, so the floor is yours. Please.
Thanks a lot for the kind introduction. Good afternoon, everybody. I would like to really acknowledge and appreciate for organizing this conference. And I would like to also acknowledge Jeroen and the other organizers to letting me present our work here. And I will talk about work we started more than a decade ago together with Jairo, who already had a beautiful talk yesterday, and Thomas. And eventually, it grew into huge international collaboration. And today I will mention some results which we did together with theorist Igor Mazin, Alan MacDonald, and Eduardo Fratkin. And also I will show some experimental results which we did together with groups of Juraj Krempasky, Pete Wedley, and Helena Reichlova. And finally, in later parts of the talk, I will also show some results from our younger colleagues, particularly from Rodrigo, Anna, Atasi, and Naira. So with this, I would like to come to motivation and take home message from my talk. And as you have seen already in the previous talks, for last 100 years, we were dividing magnetically ordered phases of matter into ferromagnetic and antiferromagnetic. And we know that they have somehow complementary advantages. For instance, ferromagnet have strong spin currents. However, at the same time, they are constrained by the net magnetization to have stray fields and gigahertz switching dynamics. So that motivated the field of antiferromagnetic spintronics and tried to look into the advantages of antiferromagnets, which are no stray fields and much faster terahertz dynamics. However, they unfortunately, because they are called antiferromagnets, many of the magnetic effects known from ferromagnets are cancelled out in antiferromagnets, giving them their name. So for instance, they have suppressed spin currents. So what we were obsessing for more than a decade, starting from 2012 with Jairo and Thomas, was whether we can combine these benefits of ferromagnets and antiferromagnets in one maybe even more magical material. And today, I will show you that when we do very systematic classification based on spin symmetries, which you already heard about as well, we can actually derive that there are not 2, but rather 3 classes of magnetic phases of matter. And besides the 2 more conventional ferromagnets and antiferromagnets, there exists another type of spin group symmetry, which corresponds to the class of altermagnets. And altermagnets are characteristic by actually combining this antiparallel dipolar order akin to antiferromagnets. But unlike antiferromagnets and more like a ferromagnet, they have this ferroically ordered spin densities. So you see that on these 2 sublattices, you have another order parameter, in this case d wave, where you see when you go around the quadrants in the space, you change the spin polarization from positive, negative, positive to negative. And exactly the same happens on the other sublattice. And today I will show you that exactly these properties and these order parameters are responsible for a lot of exciting applications. These applications and this unconventional magnetic ordering have been now also observed in these experiments and attracted also attention beyond academia. So for instance, they were highlighted in The Economist, or more recently they were selected by Science magazine as one of the top 10 breakthroughs. And I think it was quite nice to see that besides magnetism, that it was on the same list as some other amazing advances in science, for instance, from HIV medicine or from landing space rockets. So I think that for magnetism and for the topic of the conference, this is a great message, because there are rising numbers of opportunities what we can research in the coming years. So with this, let me show you outline of my talk, which is divided into 3 parts. In the first part, I will tell you about the origins of altermagnetism, and I will overview very briefly the first experiment, because it was already explained beautifully by Jairo. In the second part, I will show you spin symmetry classification, and how this led to identification of altermagnets, and I will explain what are anti-altermagnets. And finally, in the third part, I will show you some emerging directions in the fields of multiferroics, topology, and finally, I will come back do full circle from the original incentive from spintronics. I will close with the spintronics applications, which we have now thanks to altermagnets. Let me start with the first part and let me go back to the main question, which we were obsessing about with Jairo and Thomas for so long. And that's whether we can combine benefits of ferromagnets and antiferromagnets. And first, such an effect, which we wanted to understand in compensated magnets, was spontaneous Hall effect. And when you look into all the literature, also from Ukraine and also from other places in 1960s and 70s, you will see that people were expecting that when you have perfectly compensated antiferromagnetic sublattice, there should be no spontaneous Hall effect because there are some symmetries which are preventing the anomalous Hall effect. For instance, time reversal with translation, marked by this arrow, or time reversal with inversion, marked by this circle. So historically, more than a decade ago, people like Alan MacDonald and Satoru Nakatsui have looked theoretically and later experimentally into the possibility of breaking these symmetries by generating non-collinear order. However, because we were obsessed with spintronics, we wanted to have strong collinear spin coherence, so we tried to reopen the question and try to realize the symmetry breaking in collinear systems. And we realized that actually we can achieve collinear perfectly compensated magnetization density, which nevertheless exhibits additional anisotropies which alternate on the two opposite spin sublattices. And this leads to breaking these symmetries, which prevent anomalous Hall effect. And that means that you can in principle generate spontaneous Hall effect in these collinear systems as well, as we have predicted in this article from 2019 together with Jairo. And in this article, we have also indicated the possible experimental realizations of such a systems, where the trick was to take perfect antiferromagnetic sublattices, collinear, and then decorate them by non-magnetic atoms at certain positions, that this non-magnetic decoration leads consequently to these beautiful anisotropic modulations which alternate on the two opposite spin sublattices. So also, for a very long time, with our experience from antiferromagnets, we knew that a lot of effects are strongly dependent on the orientation of the null vector. So we also predicted in the Science Advances paper that depending on the orientation of the null vector, you can completely switch off or switch on the anomalous Hall effect. And that's something very unusual, very unconventional in comparison to what we have in ferromagnets. And then in collaboration with the experimental group from Jikwi Liu, we were able to very rapidly confirm this theoretical prediction. In this work on anomalous Hall effect, we also identified that a huge fraction, like 1/10 of the magnetic database from the Bilbao actually is a candidate for this unconventional crystal anomalous Hall effect. However, we still didn't have a very systematic way how to identify all the spontaneous ordering. And that brought us into more broad picture of thinking about the systems in terms of symmetries. And we found actually that there exists in literature another way how to think about magnetic systems beyond crystallographic magnetic groups. And this is called crystallographic spin groups. So what you do, as we have seen already today, for instance, in the talk from Maya, that you can take the conventional crystallographic groups and you can add first magnetism and you neglect completely spin orbit coupling, and then you end up exactly here at the crystallographic spin groups. And I will show you today that these spin groups can be super useful for classification of the magnetic orderings and also in understanding various effects in the electronic structure. So this brings me back to the Science Advances paper, where we predicted not only the anomalous Hall effect, but we also predicted this unconventional electronic structure, where we have observed that in our density functional theory calculations, we can have huge 1 electron volt spin splittings, which alternate in the Brillouin zone. So when you look in this direction, you see that the system behaves basically like a ferromagnet, because you see that for opposite wave vectors, we have the same spin. So that means that it breaks manifestly time reversal symmetry. However, when you go into perpendicular direction, you get again a huge splitting, but with perfectly opposite spin. So that means that we found in this set of works that we have this unconventional time reversal symmetry broken electronic structure. And with these predictions, we were able, in collaboration with Dominic, Helena, and others, also confirm now this anomalosal effect not only in the magnetic field, but also in its spontaneous variants. So for instance, here I am showing the experiments where our colleagues measured this beautiful zero magnetization in squid, while simultaneously they measured large remanent spontaneous anomalosal conductivity, very nicely consistent with our theoretical prediction. So having all of this at our hand a few years ago, we wanted to understand in more detail what are the systems systematically. And this brought us to the systematic classification. And by this systematic classification, by this at the time unorthodox, after 50 years revisited framework of spin group symmetries, we were able to actually introduce something new, what wasn't known in the 1960s. And after that, and the new aspect was that we realized that actually there exists such a group structure which breaks half of the lattice symmetries, and then you take the other half of the lattice symmetries and combine them with spin rotations. And this structure then leads to this Fourier ordering of the spin density, which generates this unconventional anisotropic spin densities in the direct space, and which generates also in the momentum space corresponding order parameters, which can be seen as, for instance, D, G, or I wave magnetization. So that meant that we had very systematic tool how to identify realistic material candidates and their order parameters both in direct and reciprocal space. So we try now to verify it experimentally, and here are beautiful experiments. Here I'm showing experiments from Switzerland, from Murray, where he was able to, with his beautiful ARPES, identify perfectly consistent spin splitting with our theoretical prediction. And then later also our colleagues in Nottingham were able to go into the direct space, and actually, thanks to our prediction of this unconventional time reversal symmetry breaking, they knew that there should be X-ray magnetic circular dichroism, which in many antiferromagnets is absent, but in altermagnets should be present. And they use this time reversal symmetry breaking to map the magnetic domains of altermagnets in direct space. And you see here are basically pictures of micrometer large domains, single domains of the altermagnetic manganese telluride, which are achieved by nanopatterning the manganese telluride samples into these hexagons. So this shows now that altermagnetism is not only concept, but can indeed be realized in real materials. And furthermore, we can generate large enough chunk of altermagnetic material, which can be used for all of these spintronics applications we were dreaming about more than 10 years ago together with Jairo and Thomas. So I would like to emphasize that now we have more materials, another material which we also already seen in Maya, which I believe is one of these papers here. We also observed the spin split electronic structure in this altermagnet chromium antimony, which unlike manganese telluride, which is semiconductor, chromium antimony is a metal. So this brings me to the final summary slide of this part, where I would like to summarize that we have now many reviews, because it's turned out that this is very interesting, actually several streams of research which emerge from our predictions. So one of them is apparently altermagnetism and unconventional magnetism in general. We have seen already some interesting non-collinear magnets, for instance, today in Maya's talk. Then we have seen that there is also now field of spin symmetries, and even the Bilbao crystallographic server is now implementing this framework. And finally, there is also a huge field of anomalous effects, which are very interesting for applications, as I will show you later in the talk. So with this closing of the first part, let me now go to the second part, and let me just explain you some concepts about the spin symmetries and how we can use them to classify systematically the magnetic phases of matter. So the important thing to realize is, how is it possible that these phases were missed for so long? And it turns out that people try to realize some higher partial wave magnetic order parameters, but because they were motivated by analogies with superconductors and superfluids, they looked into correlated metallic instabilities and Pomeranchuk instabilities. And it turns out that this is very difficult to realize, not only experimentally, but even theoretically. Until today, even after decades of research, there is not a single material platform where this would be realized experimentally. However, what this paper established that if there would exist some such a more generalized order parameters, that these states would be a different type of matter from conventional ferromagnetism, antiferromagnetism, as you can read from this sentence from Eduardo's paper. We have reviewed this stream of research in this recent article. But what was now the trick, how we can actually go beyond this and how we can actually realize these ordered phases? Well, the trick was to go from momentum space to direct space and actually try to build this unconventional magnet starting from the magnetization densities and their modulations in the direct space. So here I am showing you the modulations from the Science Advances paper, which I was talking about. And then when we use our spin group symmetry framework, we can do partial wave decomposition, as we did in several other papers, for instance, in this one. And you see that then you have, in addition to this antiferroic S-wave channel, you have this spatially anisotropic ferroic D-wave channel. Now we have with this demonstrated that this is starkly distinct from Pomeranchuk instabilities because you can expect many materials not only in metallic phases but also in insulating phases. So this is a clearly distinct type of ordering. And we now know, and there were also talks from Paul, for instance, there are several different realizations and very exciting theories how to approach the order parameters in the systems. I would like to highlight that besides what you already have seen and what I will talk about, we have now also methods how to stabilize the D-wave spin density on single atomic site without any dipolar order. So we are now able to have to distillate in real material systems on computers the D-wave altermagnetic magnetization density without any dipole order, which illustrate how different actually altermagnets are from ferromagnets and antiferromagnets. So with this brings me to trying to show you how the symmetry framework can be useful for this classification of these magnetization densities. And this brings me back into the foundations of group theory of magnets. And this started many decades ago with Landau, Shubnikov, and others. What they did? Well, they took the Escher antisymmetry operation of studying two-color patterns, for instance, this Escher painting of two horsemen, and you see that when you want to find symmetry operation, bringing on top of each other these two horsemen, you need to involve symmetry operation, which is called recoloring. So you need to change the color. And what Landau and others did, they assigned in magnetism this recoloring operation to time reversal. However, it turns out that there exists yet another possibility how to do it, and instead you can look into spin inversion, as it was initial ideas were laid in these articles. And today I will show you actually that both of these approaches are approximations, and depending on what you want to study, there can be different level of usefulness in them. And particularly if you want to study the different types of spontaneous symmetry breakings by these magnetization densities, it's very useful to use actually this spin inversion framework. So how does it work? Let me now compare the symmetry frameworks in these schematics on our rutile crystal. So starting from conventional crystallographic operations, I can take my 90-degree rotation. I see that this is operation of the crystal. Then I can go all the way down. And I can look into magnetic symmetries where I know that I need to act both on lattice and spin simultaneously. So when I'm rotating by 90 degrees, I need to rotate both spin and lattice. And I see that manifestly, this is not operation. This is not the symmetry of the crystal, this operation. But when I formulate these spin symmetries in the middle, I can actually formulate operations where I have a distinct symmetry operation in the crystal space, in this case 90 degrees rotation, and I can combine it with another operation of 180 degrees rotations, which is acting on the spins. And this is exactly the symmetry operation, which is responsible for these beautiful spin split Fermi surfaces, as I will show you later. And I would like to also highlight that what is another important aspect is that this is a ladder of energy scales, and we have seen it already yesterday in the beautiful talk from Daniel, that these spin group symmetries, because they are describing the non-relativistic exchange forces in your material. They correspond to actually much larger energy scale, up to 1 electron volt scale, in comparison with the relativistic magnetic symmetries, which are inherently coupling the spin and lattice degrees of freedom, and which corresponds in typical materials to micro or milli electron volt scale. So let me now show you when we now take this framework of spin symmetries and when we try to classify all possibilities. So for the sake of brevity, let me start with collinear magnets. And we will find that we can easily reconstruct the conventional ferromagnets and antiferromagnets. You see that in antiferromagnets, you have two symmetry operation types, which are corresponding to having two opposite spin sublattices. So you have one sublattice which respects all crystallographic symmetries, and then you have the other sublattice which is related to the other one by spin rotation. So this is basically a definition of antiferromagnetism. But finally, when you study all possibilities, you realize that there is this third case, which I was talking about in the introduction. And what is exciting and what is different from the conventional ferromagnets and antiferromagnets, that in this third class, you are breaking half of the original lattice symmetries already spontaneously by these exchange forces in your material. So you break half of the lattice symmetries, you take the other half and augment those with the spin rotations. And then you can look into all possibilities, and you find that you will have order parameters which have 2, 4, or 6 spin degenerate nodal surfaces on a relativistic level, which corresponds to D, G, or I wave nodal magnetization. You can, of course, look into the experiments where you can measure this in momentum space, as I have shown you in the introduction in the experiments from Uri. But you can look also in magnons, and this was now also this analogical magnon splittings in altermagnets were now also predicted and observed in this series of papers. So when you look now into this classification, there is a question that we are missing someone, yeah? Because we have here no spin order, S-wave spin order, D-wave spin order. So how about P-wave spin order? Well, it turns out that for collinear magnets, due to some spin-only symmetries, you allow only for even partial wave channels. So you cannot realize this with collinear magnets. But how about non-collinear magnets? And that's exactly something what we studied together with Anna Birk-Hellenes, Jairo, and Thomas. And what we found out that actually we can, by the spin group theory, again, find the lattices whereby distributing this spin density in a Dirac space, we can actually generate in momentum space this P-wave spin splitting with single degenerate nodal surface. And what is exciting about the systems that they are very different from what we knew before, because you see that you have a in-plane Dirac space non-collinear order, while in momentum space you have out-of-plane collinear spin order. So we have again collinear spintronics friendly spin order, which is enforced by the spin group symmetries of such a non-collinear magnet. Now let's look into the realistic materials. So here I have example of realistic material cerium nickel arsen oxide. And I would like to emphasize that now in the ordering in momentum space, we break again lattice symmetries and we have alternating spin. So that means that we have a situation like in Altermagnet. However, at the same time, you see that now for opposite wave vectors, we have opposite spins. So that's very weird, yeah? That's magnetic order, which is time reversal symmetric. So it's in a way antiferromagnetic-like, because on top of it in Dirac space, you see that the order is antiferroic because you have a time reversal with translation among the opposite spin sublattices. So because we have these hybrid properties of antiferromagnets and altermagnets, we suggested now in this recent paper to distinguish them as anti-altermagnets. So let's look now into this cerium nickel arsen oxide in a bit more detail, but I will be very brief because Daniel already mentioned that. So you see here these beautiful splittings. When you look into the band structure, you see again confirmation of the prediction I was talking about from the spin group theory, that the two in-plane direction of the spin polarizations are 0, while the out-of-plane polarization is large, and so that means that it's collinear. And you see also that the scale of the spin splitting is very large, here around Fermi level on the level of 200 millieV. So now the question is how we can detect this in experiments, and we can take even simple transport measurements. And because this ordering, as you have seen, this P wave is strongly anisotropic in the space, when we do our DFT calculations, we expect very strong up to 60% transport anisotropy. On top of it, we can look also into spintronics effects such as Edelstein effect, and because these systems are spontaneously breaking inversion symmetry, we can expect to have large Edelstein effect, and that's exactly what Atassi calculated in her DFT approach. And you see also that even when you switch on spin-orbit coupling, you have large regions in the energies where it's perfectly dominated, completely dominated by the non-relativistic effect. I would like to here highlight that similar effects were predicted also by Mengli, Jerome, and Maya and Paul, as was discussed before. And we have also here now some experimental indications of such systems, which we have seen in yesterday's beautiful talk from Ricardo. Okay, so this brings me now to the last three highlights in the last part, which will be very brief, but where I would like to just, from the many emerging research directions of altermagnetism and anti-altermagnetism, I would like to select three, which I believe are particularly exciting directions. So let me start with the first direction. That's the direction.
We have only 5 minutes.
Yes,
5 minutes.
exactly. Perfect. Thanks a lot. Thank you. So this brings me to the field or to asking a question whether we can combine the altermagnetism with multiferroicity, because altermagnets are typically so far those which we know centrosymmetric, while multiferroicity requires crystals which are chiral and which are breaking the inversion. Well, by the spin group theory, we have identified such a crystal that they can indeed exist. Here is an example of barium copper fluoride, and you see that not only that they can exist, these two orders in the same system, but in this particular symmetry class, they can even be perfectly coupled, something what we call altermagnetoelectric effect, because by applying electric field to the crystal, you can actually reorient the D-wave spin polarization. So you see I'm switching the external electric field and I'm switching in the electronic structure the spin polarization. So this is one of the dreams of having, like high temperature multiferroics. We did here the full classification again by the spin group symmetries, and we found 44 material candidates, including the famous bismuth ferrite. So here is illustration that is particularly exciting for some communities because it attracted attention, for instance, from this very nice overview cover. Now let me move from multiferroics to two dimensions. And here I would like to just show you that we can actually in two dimensions do also symmetry classification, which we did with Igor. And then we actually find that we can take a simple antiferromagnet, which is Kramer's degenerate due to the space-time inversion symmetry. But when we put it on some substrate, we actually generate altermagnetic spin splitting. And here we have some examples which we calculated also together with Raphael. And you see that in these altermagnets, you can even generate quantized spin Hall effect. So I think that's also complementary to what we have heard in the previous talks about the altermagnetic band topology. Finally, let me go back full circle and let me just briefly show you some applications in spintronics. So now when we take these beautiful altermagnetic spin densities, we can apply along this direction the electric current, and we will make it spin polarized because it behaves basically like a ferromagnet. What is curious that when you apply it along the nodal surfaces, the electric current, you will get transverse along this spin polarized current. And finally, it turns out that on top of these spin polarized currents, you will also be able to generate non-equilibrium spin polarization, so you will have some sort of non-equilibrium Edelstein effect. So let me now focus just on the first class, and let me show you what spintronics devices we can do with these longitudinal spin polarized currents. Well, because effectively this behaves as ferromagnet, you can expect that depending how you stack actually in these tri-layers the two order parameters of the altermagnets, you can have parallel or antiparallel configuration, and they should have large difference in the resistivity. So you can expect giant and tunneling magnetoresistance effects, and that's exactly what we did in this paper. Okay, so with this, if I have still 30 seconds, I would like to summarize my talk, and I would like to go back to the concepts, key concepts in magnetism. And we know that for understanding ferromagnets is very often sufficient to think about them as Curie did in terms of macroscopic magnetization, which transforms as a pseudovector. When we want to understand antiferromagnets, we need to go a la Néel to the level of atomic molecular fields. So we need to go on the sublattices. And finally, now, when we want to understand altermagnets and anti-altermagnets, which are sort of unconventional, lattice symmetry breaking counterparts, spin polarized of the conventional ferromagnets and antiferromagnets, because altermagnets are breaking time reversal symmetry, while anti-altermagnets are preserving time reversal symmetry. When we want to understand this unconventional altermagnets and anti-altermagnets, we need to go into more fine structure, and we need to understand what is happening actually with the spin density around the atoms. And when we do so, you see that we can realize these dream systems where we have perfect collinear spin polarization in momentum space, and we can have D wave or P wave spin polarization. And I have shown you today that these have many potential applications. I have highlighted only 3, but there are many more. So if you are interested, you can read some of our recent reviews. And finally, the last sentence, which I would like to highlight, that when we discover usually in physics some new phase of matter, we are super excited when we find one material realization. Here, so far, we have proposed more than 400 material candidates for altermagnets and anti-altermagnets. So I believe that we are just at the beginning of very exciting times for our magnetic community. And again, I would like to acknowledge my collaborators. Here is a picture from first SPICE conference on altermagnetism. And I would like to thank you for attention. And I'm looking forward for any questions, or please feel free also to write me an email. Thanks a lot for your attention.
Yeah, thank you. Okay, so we are almost over the time, but probably one brief question.
Excuse me, I just have a brief bibliographic question. On slide 4, I noticed that you referred to some monograph by Shubnikov. Is it the same Lev Shubnikov Degas, or
No.
maybe another physicist?
There's another Shubnikov.
Yes, these are two different scientists. Yeah.
Okay, thank you.
May I ask you a question?
I think the speaker again.
So there was one question from the online, so maybe that could be cool if it's
Some question about application. There is a big problem for the antiferromagnetic so-called thermodynamic domains. When you create some crystal and magnetic ordering in antiferromagnets, you always obtain different sign of the antiferromagnetic vector. It immediately, if you use this antiferromagnetic domains in your sample, it immediately kill all your application possibility. Is it possible some predict how to work against this situation?
Thanks a lot, Yuri. That's a fantastic question. And the answer is in this Nature paper, where we have shown a strategy with the nano patterning and small magnetic field with unconventional couplings to the G-wave order parameter, which can be used to actually mitigate these problems, and which can be used to create large enough single sign domains of altermagnetic manganese telluride. So I'm happy also to discuss more later, but I don't want to distract the schedule. So that's my brief answer. Thanks a lot for the question.
Thank you.